In the last activity, we learned that there is a way to write the exact side length of a square even when the side length is not a whole number. In this next activity, we'll be looking at more tilted squares and determining their exact side lengths. We will also look at patterns in a table of side lengths and areas to help us better estimate side lengths that are not whole numbers and to better understand the relationship between squares and square roots. Let's take a look at this tilted square. It should look familiar as it is the same tilted square from the last activity. First, we're going to find the area of square A using the surround and subtract method we learned last week. When I surround square A in a larger square, my larger square has a side length of 7. The area of the larger red square is 7 squared, or 49. However, there is extra space in the shape of triangles in the corners of the larger square that need to be subtracted out. The base of each triangle is 2, and the height of each triangle is 5. So my equation for the area of each triangle is 1/2 times 2 times 5, which equals 5. Since there are 4 triangles, I can multiply 5 times 4 for a total of 20 extra square units that need to be subtracted from the larger square. 49 minus 20 is 29, so the area of square A is 29. In order to find the side length of square A, I need to figure out what number, when multiplied by itself, equals 29. I know that there is no whole number that will give me 29 when I multiply it by itself, and I remember from the last activity that it was close to 5.3, but there's a way to write the exact side length. The side length is the square root of the area, so the area for square A is the square root of 29. Now we're going to complete a table with missing side lengths and areas. Notice the table is missing some values in both the side length row and the area row. We are going to start by filling in the area row. Remember, the area of a square is calculated by squaring its side length. So 0.5 squared is equal to 0.25. 1.5 squared is equal to 2.25. 2.5 squared is equal to 6.25. 3.5 squared is equal to 12.25, and so on. Now for the top row, I need to find the side length when I am given the area. If I have a square with an area of 1, then what number squared is equal to 1? The answer is 1. If I have a square with an area of 4, then what must a side length be? Well, 2 squared is 4, so the side length is 2. So when I'm trying to find the number that was squared to get the area, I'm actually finding the square root of the area. So for the next one, the square root of 9 is 3, because 3 squared is 9. 4 squared is 16. 5 squared is 25. 6 squared is 36. 7 squared is 49. And 8 squared is 64. Now let's see what it would look like if I graph all of these ordered pairs. Now compare that to the graph of the area as a function of side length. This is the graph of the function x squared because side length squared is equal to the area of a square. Remember we found that square A had an area of 29. Therefore, the side length of square A was the square root of 29. Let's find this on our graph. A square with an area of 29 would be represented by this point on the graph. We see that that point has a side length a little smaller than 5.5. If we think back to the warm-up, we estimated that the side length of the square was 5.3, but here we can see that a more accurate approximation is actually closer to 5.4.